No.
So Jim, have you met Soheyla yet?
I don't think so. No. Where would I have? I mean, I haven't, been out of town in forever, but maybe virtually. Were there some talks that I should have seen already?
Yes, she finished her PhD about 4 years ago. So she was on the conference circuit before the apocalypse hit.
Well, maybe I have, in fact. Okay, I don't know. Yeah.
Well, this is really just like an in-person conference because I have to ask Jim to stop talking so I can start the talk on time.
Just perfect. All right, I'll mute.
Shut up, Jim.
Okay. It is welcome to the Western Hemisphere Colloquium on Geometry and Physics. It's my pleasure to introduce today's speaker. But before I do that, I want to just remind you of the protocols. Is that during the talk, if you have questions, please put them in the chat under chat to all. I will aggregate questions and break into ask them throughout the talk. At the end of the talk, there will be you will use the raise hand feature if you have questions, and then I will call on you, and then you can unmute and ask your question to the speaker. So without further ado, today's speaker, we're pleased to have Richard Thomas, who will talk about Nonabelian DT theory from abelian DT theory.
Okay, thank you. Thanks, Sheldon. Thanks for the invitation. So this is joint work in progress with Soheyla Feyzbakhsh, and there's 2 papers on the arXiv and 1 to come. So non-abelian refers to high rank, and abelian refers to rank 1. So I'm going to talk about DT invariants, and I'm going to call them DT invariants because, I mean, mainly because my ego is out of control, but also because as a graduate student, I used to see Donaldson go through agonies trying to avoid saying Donaldson invariants of smooth 4 manifolds. And it would have just been easier if he just called them Donaldson invariants rather than nonlinear polynomial Yang-Mills something invariants. So I'm going to talk about Joyce's generalized DT invariants and then try and explain the rough idea of what we're doing in these papers. So how to pass from rank R to lower rank. The aim is to get to rank 1 because that has something to do with Gromov-Witten invariants, for instance, and because it's the abelian theory. For now, what's written in the second paper I listed is how to get down to rank 0, in fact. So our method takes rank R DT theory and it spits out lower ranks all the way down to 0. So for now, by an induction, it's easiest to get down to rank 0. And in fact, the easiest case to explain where everything works very simply is in passing from rank 1 to rank 0. So I'll explain that. And then I'll explain our general results for high rank. And then passing, we managed to express all of DT theory in terms of rank 0 DT theory. That's what's written on the arXiv. And then the thing that's still to appear is trying to express everything in terms of rank 1 DT theory. That's the work still in progress, and I'll explain that at the end. And then I'll explain some of the technicalities, just a very sketchy picture of how we do it, like what our techniques are using the weak stability conditions of Bayer, Macri, and Toda, and wall crossing. And then right at the end, I'll explain, once we've got everything in rank 0, how we intend to, or how we're expressing that in terms of rank 1. Okay. All right, so throughout, I'm going to be on a Calabi-Yau threefold. I'm going to have a fixed line bundle on it, or its first Chern class I'm calling H, hyperplane class. So this is just a Kähler form, an integral Kähler form, so that I can define stability. And if you vary it, then the notion of stability changes and you get wall crossing phenomena, but we come to that later. And there's a technical condition that you don't have to worry about, that the Calabi-Yau threefold should satisfy the Bogomolov-Giesecke conjecture, of Biomacritoda. So this is this is a bound on an upper bound on the third Chern class of weak stable objects. So the usual Bogomolov inequality says that slope stable sheaves have a lower bound on their second Chern class or second Chern character. And this is an analog for the third Chern character. And it's been proved for various Calabi-Yau threefolds, by no means all of them though, but in particular it is true by work of Chunyi Li in the cases we need for the quintic threefolds. So this isn't an empty theory. But anyway, that's just a technical condition we need. And throughout, we're going to fix a Chern character and consider semi-stable bundles or sheaves or complexes of sheaves with that Chern character. So throughout, that's just fixed. And I have to tell you what semi-stable means or stable means. Okay, so there's many notions of stability and we'll use many of them. And the ones we use will all be written in terms of some central charge. So this is, I guess, notation from the physicists. Writing the central charge as sort of in polar coordinates as a mass and a phase, then the slope of E is the slope of that complex number. So it's the tan of the phase. And then stability is an inequality like this. It says when you have a sub-object, sub-sheaf, let's say, then the slope should be smaller, and if you have a quotient sheaf, the slope should be bigger. In fact, we'll work in various funky abelian categories where what you mean by sub-object is a bit tricky. But for now, just think about sub-sheaves of sheaves. In general, that won't be the right notion, but that's okay. Okay, so for instance, classic slope stability of, I guess, Mumford comes from taking this central charge, so the degree of the bundle, and plus I times the rank. So that's where this H is entering this Kähler form to define the stability. And then another version of stability is you take this central charge. So the first term is a polynomial in n of degree 3, and that less equal 2 means throw away the degree 3 term and use the degrees 2, 1, and 0 parts. And the degree 3 term is essentially the imaginary part there, the rank. Or that's the coefficient. Okay, and that gives something called Giesecke stability. And you can think about slope stability, that's fine. Giesecke stability is a refinement that's more useful in algebraic geometry. And moduli spaces behave better and deformation theory behaves better. Okay, so what are DT invariants? So roughly, there's this constraint originally in the original theory 20 odd years ago, which was that you should only take Chern classes and stability conditions or Kähler forms so that Giesecke semi-stability implies Giesecke stability. So there's no strictly semi-stables. And one way of thinking about that is that strictly semi-stables tend to have big automorphism groups. And we want things which only have automorphisms, multiples of the identity, just scalar automorphisms. We'll remove this constraint later, but okay, but for now, so we're going to take a nice moduli space of Giesecke stable sheaves. There'll be no strictly semi-stables. And there's this so-called DT invariant, which is an integer, and it counts these Giesecke stable sheaves of fixed Chern character. And here's the technical stuff for Jim. So it's that the moduli space is a projective scheme. So that's because there's no strictly semi-stables. It has something called a perfect obstruction theory of virtual dimension 0, and therefore a zero-dimensional virtual cycle. And the length of that cycle is the DT invariant. Okay, and if you're a physicist, then what's probably more familiar is that holomorphic bundles are critical points of the holomorphic Chern-Simons functional. So you might expect critical points to be isolated, and that's really what all those fancy words in the paragraph above mean. Even though they're not isolated, there's something we can do, like perturbing, but it's not really. We're in algebraic geometry, we don't do that. But we can pretend we can perturb and make them isolated, and then we just count them. But the way we perturb is a bit more complicated, and particularly you get negative numbers for this DT invariant. And you should think of it as just the Euler characteristic of the moduli space. There's a sign, and in general, Branes showed how to make this much more precise. So if the moduli space is smooth, it really is the Euler characteristic up to this sign. And even if it's not, he showed that at every point of the moduli space, you can assign a multiplicity, which tells you roughly how singular the moduli space is at that point. It's an integer. And then you take the weighted Euler characteristic. So you weight by that integer. So you take the locus where the chi-Branes invariant multiplicity is I, and you weight it by multiplying it by I. So you take its Euler characteristic, multiply by I. But you can ignore this. Throughout the talk, I'll just pretend that we're using Euler characteristics. In fact, everything can be done properly with proper DT invariants rather than these naive DT invariants. But for the purpose of the talk, we'll just pretend the DT invariant is an Euler characteristic. Okay, so that's sort of the classical theory. Maybe I emphasize this is in any rank. So in the physics literature, somehow DT has come to mean rank 1. This is MNOP's fault. But in reality, the theory was defined in arbitrary rank from the beginning. So it's sort of a Nonabelian theory in some sense. And then if you do have strictly semi-stable sheaves, things are much more complicated. And the reason for that is that they're made up of stable objects in complicated ways. You can take direct sums of stable objects and iterated extensions of stable objects of the same slope to produce semi-stable objects. And more generally, there's something called a Jordan-Holder filtration by stable objects. And these have large automorphism groups. And using this naive Euler characteristic approach, what you would like to do is count a sheaf with an automorphism group G, not as 1 or plus or minus 1, but as 1 over the Euler characteristic of G. That turns out to be the right thing to do to get deformation invariant results, get nice answers. And of course, the Euler characteristic of G is 0, so you can't do that. So Joyce and Kontsevich-Soiberman found a way of sort of inverting this process. So if you think of taking stable objects and then their direct sums or direct sums of stable objects of the same phase as being some kind of symmetric power functor or exponential or something, then they take some, or plothistic exponential, if you want to get fancy, they take some kind of plothistic logarithm to sort of, so that we can pretend after they take this logarithm that we're counting things with automorphism groups of rank 1, just scalar automorphisms. In reality, it's more complicated than that. It's a very complicated theory, but there is such a theory. And this allows them to define invariants. So Joyce and Song defined a rational number, not an integer anymore, which reduces to the old integer when there are no strictly semi-stables. And Kontsevich and Soiberman worked in more generality, so they were defining refined and categorified, fancier DT invariants, counting complexes and so on. But some of their theory at the time was conjectural, whereas Joyce Song's all nailed on. But now, pretty much, I think all of Kontsevich-Soiberman's conjectures have been proved. Their absence of poles, integrality conjectures, orientation data. So now probably Kontsevich-Soiberman invariants are probably completely well-defined, and all of the machinery works well enough to make everything that I'm going to do in this talk work in their setting. But I'm not an expert on that theory, so I'm going to stick with the Joycean theory. Okay, so we have these rational numbers. Forget about everything I've said up till now. Just pretend they're the Euler characteristic of the moduli space. They're invariant under deformations of X. I can move X a little bit, its complex structure, and these invariants won't change. But if I move the stability condition, they also generically won't change usually, but every now and again, the stability condition will cross a wall in the space of all stability conditions. And the invariance will change in a controlled way called a wall crossing formula. So let me say something about that. So, Sheldon, are there any questions?
There have been no questions in the chat, so please continue.
Okay, great. Or maybe not great. No, and no one's listening. That's fine. Right. So here's the simplest wall crossing formula. So suppose you have a bundle and it's an extension by two other bundles, A and B, and they're stable. So they themselves don't undergo any wall crossing. If the more complicated situation is where they're also semi-stable. But anyway, let's take this as the simplest case. And suppose we can vary the stability condition so that the slopes of A and B cross. So, you know, just below the wall, the slope of A is less than the slope of B, and just above the wall, the slope of A is bigger than the slope of B. There we are. So then just below the wall, F will actually be stable, assuming this is a non-trivial extension. And just above the wall, F will be destabilized by having this sub-object A of greater slope than the quotient object B. But then what will happen is extensions in the opposite direction, where you swap A and B, they'll become stable on the other side of the wall. So what you find on crossing the wall is that we lose all the extensions star. Well, they form a vector space called x to 1ba. Don't worry if you don't know what that is. But that classifies the extensions up to scale because of the automorphisms of the problem. So we end up with a projective space of extensions. And we lose those, but we get the extensions in the opposite direction. And you can't control these. These extension groups can jump around. As you vary A and B, they'll jump around. They're not topological or anything. But their Euler characteristic, so the Euler characteristic of this one is just the dimension of the x1 space. So we call that little x1. And so what you find is at the level of Euler characteristics, what happens is you lose the Euler characteristic of this and you gain the Euler characteristic of that. And even though you have no control over either of these numbers, their alternating sum, you do have complete control over. That's topological. So by S-duality, the second one is x2 from B to A. And now what you have is the alternating sum of x groups, of dimensions of x groups between B and A. Because there's no HOMs from B to A because of this condition on stability. And there's no HOMs from A to B for the same reason. And therefore by S-duality, there's no x3s from B to A. So anyway, this turns out to be all the alternating sums, the entire alternating sum of x groups, dimensions of x groups from B to A. And so that's given by a topological quantity, by a Riemann-Roch formula. So it's given by the integral over x of the Chern character of B dual times the Chern character of A times the Todd class of x. So there's just a Riemann-Roch formula. So we have complete control. Even though we don't have control of what we lose and what we gain, we have control of the difference. And so what you find is this Joyce invariant, this wall crossing formula, says that above the wall, the Joyce invariant is the same as the one below the wall. That comes from all the sheaves which don't get affected, don't have any extensions like this. Plus, and then up to that sign, which we'll always ignore, this topological constant that I just derived for you, times by the number of sheaves of type A and the number of sheaves of the same Chern character as B. So for every A and B, you get this argument that I just said. So that's the simplest possible wall crossing formula. Are there any questions about that?
Yeah, no questions.
So that's a really great thing because it involves only topological quantities and other DT invariants, generalized DT invariants. These J's here, it could be J plus or J minus, doesn't matter because A and B don't undergo any wall crossing themselves. And then you have more complicated wall crossings where, F might be made up of 3 pieces instead of 2. But the same principle applies. You end up now with a correction term with a topological quantity multiplied by a cubic in DT invariant. So you'll have a JA, a JB, and a JC. And similarly, if it splits into 4 pieces and so on. And these topological constants and the coefficients and so on are all very complicated. Deriving the formula in general, the case I gave you is rather easy, but in the higher order terms are very complicated. But we won't need them. We just need their existence. We just need to know they exist. So that's wall crossing. That's how these invariants change as you change stability conditions. I can see the chat's flashing at me now. Maybe I shouldn't read this. There'll be more comments. Yeah, that's right. Yeah, thank you. Sheldon's answered for me. Okay. Okay, so here's the rough idea. This is really the only slide that matters in this talk. Pay attention. What we do, we twist our sheaves by this very positive line bundle, ON. So we twist by O1 n times. So we make sure that they have no higher cohomology. And then we replace them by the co-kernel of a section of that twisted bundle. Okay, so you take your bundle, it has lots of maps from this very negative line bundle, and you consider their co-kernels. And that has rank 1 less. So if E has rank R, then F has rank R minus 1. Okay, and the Chern character of F is just the Chern character of E that we started with, minus this exponential of the Kähler form. Now, to a first approximation, for the purposes of this slide, you should just suppose that all the E's and F's are stable, while whenever S is non-zero. In reality, that's not true, and they give us higher order corrections, which we'll come to. But to a first approximation, to get the idea of what we're doing, just pretend that there's no stability issues. And then what you find is, this takes some work, but because n is so large, what you find is that any of these F's, as you vary the sheaf F in its moduli space, it always comes from an E and an S. You can always reconstruct E and S from F. That's just because n is very large. They're the same data essentially. So the moduli of F's, that's this moduli of in Chern character Cn, is just a projective bundle over the moduli of E's, because it's the space of E's, it's the space of pairs E, comma S, and S lives in a vector space. It's the space of sections of E twisted by n. Here we are. But really, because E's got a C star of automorphisms, and S is non-zero, really it's the projective space of this vector space. And then as you vary over the moduli space, this projective space varies, so you get a projective space bundle. All right, so what you find is the moduli space of F's is this nice, simple, smooth bundle over the moduli space of E's, if you're in some fantasy situation where stability doesn't matter. Okay, and this capital N here is again some topological number. So what you find is that if you just take Euler characteristics, then up to this sign, which should be grayed out really, the DT invariant or Joyce song invariant of counting the F's is just because it's just the Euler characteristic of the fiber, that's big N, times the Euler characteristic of the base, which is the DT invariant counting the E's. Okay, and that's done what we wanted. That has expressed this DT invariant, any DT invariant, JC, in rank R, in terms of, by dividing by this constant, a DT invariant in rank R minus 1. All right, so that's the rough idea. And now, maybe I should say, this is actually a wall crossing formula. I haven't made it look like that, but we'll see later this is actually an instance of the wall crossing that I described on the previous slide, but not in the abelian category of coherent sheaves, but in some funky, crazy abelian category. We come to that. Okay, and then actually there's higher order correction terms and so on, but again, the idea is to try and show that they're all controllable. They're all governed by topological constants and other Joyce song or DT invariants. And then what we want to do is, in reality, this won't be true because of stability issues. So we're going to have to cross lots of walls to get to the stability condition we care about, which is Giesecke stability. And again, when we do so, each time we cross a wall, that's going to generate more correction terms. So what the technical heart of the paper is about is setting up various inductions to show that there's only finitely many walls, and that every time we cross a wall and spit out various pieces that destabilize us and so on, there's only finitely many walls for those pieces as well. And we want to show that every piece that shows up has rank less equal r minus 1. So it doesn't affect this formula. It still gives us that this DT invariant in rank r can be written in terms of things in rank r minus 1 and lower ranks. They'll be the correction terms. And so the induction is used to show that you only ever get lower ranks each time you do this. And you only ever get sheaves because we're really working in the derived category. So you might be getting all kinds of complexes and sheaves of higher rank and all kinds of things. So we try and control all that. But that's the technical, that's what we have to do in the rest of this talk in some sense, although I won't give too many details. I wanted to say something else, but I've forgotten what it was now. So also, of course, we have to, this isn't quite true. It's not really a Pn-1 bundle because there might be semi-stables and it gets more complicated. But again, the idea is that only ever generates terms that we can handle. Ah, yeah, I remember what I was going to say. These higher order correction terms, we eventually prove are of lower rank. So that's great. That gives us what we want. But they include rank 0. So we can't get down to rank 1 naively in this way. So what happens is we get down to ranks r minus 1 all the way down to 0. And then we can do an induction, do it again. And eventually what we can get down to is rank 0. Then we have to do a separate argument to get to rank 1, which we come to at the end. Okay, so that at least motivates why it might be interesting to try and understand how we go from rank 1 to rank 0. And this is interesting for other reasons. And everything works perfectly here. It's incredible. It's a great surprise to me. But there's no higher order corrections. There's no semi-stability. There's no nothing. So here's the statement. So in rank 1, we're interested in moduli spaces of ideal sheaves. So these are just rank 1 sheaves with a singularity along curves and points in X. And these are the things that physicists call DT invariants that count these guys. So there's no semi-stables, so we get integers. And these are the things which should be equivalent to Gromov-Witten invariants. Now, if you do our process from the previous page, what do? You have to take a section of this ideal sheaf twisted up by this ON line bundle. Okay, so such a section gives you, by ignoring Z, it just gives you a function or a section of the ON line bundle on X, which cuts out a divisor of degree n. Okay, so this is a very positive divisor in X. And then the co-kernel of this section is the, so thought of as a map from O minus, let me just go back, thought of as a map from O minus n to my ideal sheaf. The co-kernel of the section is something just supported on the divisor. And what it is you take the ideal sheaf on the divisor, as Z lies in the divisor, and then you push that forward to give you a rank 0 sheaf on X, which is 0 away from the divisor. It's some kind of Dirac delta on the divisor, except it's all singular along Z. Okay. So I'm using straight I to be ideal sheaves on D and curly I to be ideal sheaves on X. And in this case, it turns out that everything is stable and they're the only stable sheaves of this form. So the moduli space really is a Pn-1 bundle. And you get, the sign is grayed out this time, and you get that the DT invariant counting these so-called D4, D2, D0 branes in this very positive class D in ON is just a topological constant times the DT invariant counting ideal sheaves, or the MNOP invariant, the invariant that Malik-Nekrasov, Kunkov-Pandra-Panda conjecture is equal to, well, is equivalent to Gromf-Witten invariance. So what this statement is, the reason it's surprising is that you could imagine other sheaves in this same class Cn. So other sheaves with the same topology as F. So for instance, you might take a divisor which is half the degree, if n is even, and then stick a rank 2 bundle on it. And what the statement is that must be unstable because this n is so large. I mean, that could be stable if n was small, but when n is so large, such a thing always has to be unstable because it isn't of the form described by this result here. And conversely, all of these co-kernels are stable. All right, so that in that case, what you end up with is this very simple formula, and it says that MNOP invariants or Gromov-Witten invariants essentially can be written in terms of these invariants counting these D4, D2, D0 branes. And those, you know, I shouldn't talk about things I don't understand in front of physicists who understand it much better than me, but there's this S-duality conjecture that those invariants should be governed by vector-valued modular forms. You'll know those initials better than me. Whereas the invariants that we relate them to just count curves and points in X, and therefore are equivalent to Gromf-Witten invariants. And this MNOP conjecture is actually proved now for most Calabi-Yau threefolds by Pandra-Panda and Pixton. So this is saying that Gromov-Witten invariants should be governed by certain vector-valued modular forms, and I don't think this has really been exploited in the maths literature. I've not seen anything in physics literature either. Maybe people can tell me otherwise. Okay, so that was an aside. Now we want to get back to how we carry out this so-called rough idea and what the corrections are. No, first I'm going to state the theorem. There you go. So we get down to rank 0 and we state this. What we end up with is a theorem. This is a very abstract existence theorem, that there's some universal function such that any given DT invariant can be written as a function of DT invariants of rank 0, pure dimension 2 as it happens. So these are really D4, D2, D0 branes. The D4 is non-zero. And these universal polynomials depend only on the topology of X. And we've no idea what they look like. It's entirely an abstract existence theorem. It's not explicit. But to go from this, which is expressing everything in terms of rank 0, to expressing everything in terms of rank 1, which is really what we want to do and what my title was about, what's left is to express rank 0 in terms of rank 1. And I discussed that on the last slide. And then just a comment, today I found out that it may be that this paper of Del Zotto, Nekrasov, Piazza-Lunga, and Zabzin gives a prediction for maybe formulae like this, at least in the toric case. So they may give explicit formulae, but we certainly have nothing like that. We just have an abstract existence there. Okay, so before I get on to the proof or how we go about it, which won't be too technical, but I'll just give you some idea. Are there any questions about the theorem?
No questions in the.
No, we're good. Thank you. Okay, so we use these weak stability conditions. These are a bit like slope stability, in that slope stability only sees the first Chern class and the rank. It doesn't see second Chern class, third Chern class. That's what weak means here. They're also, these guys are a bit stronger than that, but they don't see the third Chern class. So they depend on two parameters, which we're going to move to get wall crossing. Unfortunately, I apologize, we don't work with just sheaves. We work in a certain abelian category of complexes of sheaves. Well, they do. This is Macri-Toda's fault, not mine. Where these complexes have -1th cohomology, so this is the kernel of this complex, whose slope, or maximal slope, is less than b, and their co-kernel, their 0th cohomology, has minimal slope bigger than b. They're made up of, yeah, this is, you know, if I had a whole other hour and a whole different talk, I could talk about tilting of abelian hearts in triangulated categories, and it's all very, it's quite nice. It's quite easy to motivate this. Tom Bridgeling gives great talks about this, but I don't really have time for it here. So just think of this as some technical, mathematical, abstract nonsense that mathematicians do, and pretend you're working with sheaves. It's not so bad. And on this, we use a certain central charge. And as I say, this doesn't see Ch3. It only sees first Chern character, the rank, second Chern character, and rank. Okay, and then B and W are parameters in this. And so this is our slope function here. Okay, imaginary over real. And it can take the value plus infinity. And we assume this Bogomolov-Giesecke conjecture, as I mentioned before. So there's a certain upper bound on Ch3 for semi-stable objects. So this is where it does see the third Chern character. Just as slope stability appears not to see the second Chern character, but yet slope stable objects satisfy the Bogomolov, the original Bogomolov inequality, which says that the second Chern class is basically bigger than 0 or something. So it's a lower bound on Ch2. This is an upper bound on Ch3. Okay, so here it is. If you give a damn, you shouldn't. It's a formula. It depends on B and W, and it's an upper bound for this C3 here. And it's a sufficient condition for the existence of Bridgeland stability conditions. So that's why they introduced it. When this holds, they can prove the existence of Bridgeland stability conditions on the Calabi-Yau threefold. And it's been proved for that reason on some Calabi-Yau threefolds. But we are not going to use Bridgeland stability conditions, or only tangentially. We're using these weak stability conditions and this inequality. And so, for instance, Chunyi Lee has proved that it holds more or less on the quintic threefold, certainly enough for our purposes. Okay, so forget all that. What's the picture? So the picture is the following. You can sort of plot objects or topological quantities of these objects on a two-dimensional diagram on the same axes as you plot B and W. So the picture looks like this. So the shaded area is where W is bigger than B squared over 2. So that was what I told you needed for a stability condition. So the shaded area is the space of weak stability conditions. There's my weak stability condition, BW. And then I plot these topological invariants of my sheaves, or complexes of sheaves. And when they're semi-stable, they always lie outside the parabola. That's because of the classical Bogomolov inequality. And then what you find is, if you plot things in this way that I've described, a very nice feature happens, is that all walls are linear. They're just lines. And whenever, so let's suppose E becomes semi-stable on this wall, then what happens is the things which destabilize it, so that sit in some destabilizing exact sequence with it, like F, they lie on the same wall, and the wall goes through the stability condition that I'm using, the one that makes E strictly semi-stable. And I can move along this wall, so I can move B and W anywhere along this wall, and the same will be true. F will continue to semi-destabilize E. it will continue to be in that abelian category I told you on the previous slide. We use that a lot. That constrains things a great deal. But anyway, the picture looks like this. So you get these walls, which are all straight lines. And if you're interested in the stability of E, they're all straight lines going through this pi of E. So it becomes rather easy to analyze-ish. And the Bogomolov-Giesecke conjecture here, this is also linear in B and W, notice. And so that also gives you a line through pi of E. It also goes through pi of E. The Bogomolov-Giesecke inequality for E goes through pi of E. And what you find is that what that means is, what that inequality states is that basically above that line, it's possible for E to be stable, but below that line, E must be unstable. All right. So here's what happens. This is what the geometry looks like. We have this thing called the large volume chamber. So results essentially of Bridgeland show that beyond a certain wall, this upper wall here, anything that's weak semistable with respect to B and W is something called tilt semistable. So don't worry about that. Pretend it's either slope or Giesecke semistable. It's something in between. For Jim and other mathematicians, it's whereas slope stability uses the first two terms of the Hilbert polynomial, and Giesecke stability uses all four of them. Tilt stability uses the first three. So it's exactly in between slope stability and Giesecke stability. And then there's a further wall crossing which goes from this tilt stability to Giesecke stability. And I won't talk about it. It doesn't change anything. You're just dealing with sheaves up here. You're not dealing with complexes. Everything's nice and controlled. So more or less, if we can get up here, this is heaven. This means everything's under control. And then as we go down, there's a finite number of walls. That's important. Then there's a very important wall, because it's red. We call the Joyce song wall, which I'll talk about on the next slide. Then there's another finite number of walls. Everything's finite. And then there's this Bogomolov-Giesecke inequality, which says that below this blue wall, everything's unstable. So if you get down here, you're good as well. You know that everything in our class Cn is unstable, and so all invariants are 0. And so we're doing wall crossing here, not in the original class C of rank R, but in this class Cn of rank R minus 1. This is where the F's lay, the co-kernels of sections of our sheaves of class C. Okay, so I've got to tell you mainly about this Joyce song wall. And this Joyce song wall goes through the line bundle O minus n. If you remember, my sheaves F were made up of the original sheaves E of rank R and these O minus n's. They were the co-kernel of a map from O minus n to E. And this is the wall on which those sequences destabilize my sheaves F. So let me explain that. So the Joyce song wall is where the slopes of F and this line bundle, but shifted, coincide. So this shift just means a complex, not in degree 0, but shifted to be in degree -1. So I don't know, physicists might say an anti-brane instead of a brane or something like that. So in K theory, it's minus the sheaf O minus n. It's not the sheaf. So remember these exact sequences we had. So we were taking sections of E and getting a co-kernel. In the derived category, you can rotate these. So you, in that abelian category, that funky abelian category that I wrote down, this is not an exact sequence because these are objects. This object, O minus n, is not in that category, but the shift is. So actually, you should rotate it. This is about a bit like turning a short exact sequence into a long exact sequence. And what you get is something called an exact triangle. And now F is in the middle. And it says that F is made up of E minus O minus n, or plus shifted O minus n. So just as in this picture, you could say F is E minus O minus n. That's what's going on here. F is E plus minus O minus n, this shift of O minus n. And it turns out that this exact triangle is an exact sequence in our crazy category. And it's what destabilizes as we cross this red Joyce-Song wall. So below the wall, any sheaf that can be written in such an exact triangle gets destabilized by it. And above the wall, it's stable if and only if E is semi-stable and the section of E here, or in other words, the extension class of this triangle, does not factor through any semi-destabilizing subsheaf. So don't worry about that, it's just some technical thing. But this gives you a wall crossing formula. So this is basically, when I was telling you about the rough idea, and I was telling you that the space of E's, sorry, the space of F's was a Pn-1 bundle over the space of E's, and therefore I could relate the invariants. Really, that was a wall crossing formula, but for this crazy exact triangle. So it was saying the space of F's is made up of the extensions of these anti-sheaves and these sheaves. And when you work out the x1s, or the space of extensions from here to here, it is, of course, just the space of sections of E twisted by n. So it's the space of these maps here. So that analysis that I did relating the E's and the F's is a wall crossing formula, but in this crazy category. And the advantage of that is it means that even though that analysis I did before wasn't true, there were, it was an approximation. Now we can make it more exact because the wall crossing formula tells us what the corrections are. All right. So what happens is, crossing this Joyce-Song wall, the wall crossing formula tells us that the invariance above the wall, which is not quite where we want to be yet. Remember, we want to go all the way to the large volume chamber, so we're not there yet. But just above the wall, the invariants equal the invariance just below the wall, plus this correction given by all the sections and all the sections of sheaves E times by the number of those sheaves E, that's the sort of Joyce invariant counting those sheaves E, plus higher order corrections. And they come from the sections which don't satisfy this condition. So they live in some subsheaf of E which has the same slope of E. Or maybe they live in some subsheaf which lives in some subsheaf which lives in E, and they all have the same slope and so on. And each time you do that one more time, you get quadratic, cubic, quartic, and so on terms. But you only get finitely many. They're always of the form Joyce invariant, products of Joyce invariants times topological constants. Okay, and even though we're not really dealing with sheaves here, we've really got sort of complexes of sheaves and shifted sheaves. This condition here means that all the higher order corrections really correspond to subsheaves of E, and therefore they're lower rank. So what happens is all these higher order corrections have lower rank, and that's what we want. All right, so that's crossing, that's the Joyce-Song wall, that's the main point, that's the important bit. And now what we do is we wall cross up and down to infinity, up infinite, sort of heaven and hell, up and down, to make this formula into the formula we actually want. So what we're going to do is we're going to take this first term up to infinity to make it look like tilt stability or Giesecke stability. We're going to take this term, the one just below the Joyce-Song wall, down to hell, where it'll become 0. Of course, along the way, it'll spew out lots of other higher order terms, but we'll try and control them. And then similarly, all these terms will send up to infinity to the large volume chamber to try and get Giesecke stability for them. And what we have to do is, at every stage, we have to check that each time we cross a wall and we spew out lots of shrapnel, we have to show that that shrapnel is just sheaves. It counts sheaves, no complexes of sheaves, and that those sheaves have lower rank. They never rank bigger than R. That's not too bad once you know there's no complexes of sheaves, but they're not rank R either. That's harder. All right. So what we proved that all further wall crossings. So let me show you on the picture and remind you of the picture again. Oh, I've done something wrong. go on. So in this picture, I spent a lot of time crossing this red wall. Then what I have to do is I have some invariants below the wall. I just send them down here until they become 0. And each time I cross a wall, I spit out this shrapnel of sort of destabilizing factors. And every single destabilizing factor that I spit out, I send up to infinity to try and relate it to Giesecke or tilt-stable invariants up here. And eventually I pass so many walls that I've got nothing left, because down here everything's unstable. And I've sent everything else up to infinity. And then similarly, the invariants above the wall, I just go up to infinity for them. Each time I cross a wall, I spit out all this stuff, and I make that cross walls as well, and just show that everything is finite. This whole process doesn't generate infinitely many walls, and that at every stage we get sheaves of lower rank. Okay, so that's that statement there. All the further wall crossings involve only sheaves. So there's no more complexes of sheaves, no more shifts, no more funky stuff. That only happens. The only place where we leave the world of sheaves is when we cross that red Joyce song wall. And these wall crossings spit out all these destabilizing pieces. And we wall cross all of those upwards to the large volume chamber. And their wall crossing also only involves sheaves. So the rank never increases. And then there's one last thing, which is that each stage, a certain invariant called the H discriminant decreases strictly until it gets to 0. And it can't drop below 0. It's always bigger equals 0 by something called the classical Bogomolov inequality. So a double induction on rank and this discriminant turns our wall crossing formula. So this was just above Joyce-Song wall, this was just below, and this was the correction term, into eventually a formula for invariance at infinity in the large volume chamber, formula below the BG line where everything's 0, this correction, and then lots of higher order terms, but the higher order terms are all nice topological functions, polynomial functions on Joyce invariants of lower rank. All right, so we're ending up with exactly what we want. We're managing to get the invariant in rank R here in terms of invariance of ranks, lower ranks. And then we go from a further wall crossing from this tilt stability in the large volume limit to Giesecke stability. And so we get the formula we want. And then the last slide. So any questions before I do the last slide?
There's a question from Tudor, checking his understanding that strict decreasing rank ensures you won't get infinitely many walls like an accumulation point.
Yeah, so the rank does not strictly decrease because of all these rank 0 sheaves we keep spitting out. This is the big problem with what we do. This is why we can't get down to rank 1. We go down to rank 0. It's because we keep spitting out rank 0 sheaves as well. So actually, that's why we need another invariant, so this discriminant, to make sure that everything terminates and everything's finite. But the idea of your question is exactly correct, but we have to use this discriminant because this is the thing that strictly decreases. The rank does not, it only semi-decreases. Is that good?
Another question from Jim, from rank 1 to rank 0, is there only the red wall?
I thought we weren't letting Jim speak.
Well, we can let
Okay. He can speak virtually.
Okay.
Let me read his question. From rank 1 to rank 0, there is only the red wall. Correct, Jim? Yes, that was right. There are no walls above or below. That's what's so amazing. Yeah, good point. Thank you. I should have said that. Cool. Okay, so the ongoing work that we're very confident about, and we've got most of it now, but we should be careful. This isn't proved or written down yet. Most of it is, but okay. So here, what we want to do now is we've expressed all of high rank DT theory in terms of rank 0 by induction. So now we want to go from rank 0 to rank 1. Well, actually, what we do is just the same thing as before. We just take sections again, and we form these Fs from these sections. So in other words, what we do is we go from rank 0 to rank -1, not to rank 1. Okay, that's a typo. So what we do is we replace E now by this complex of sheaves. O minus n goes to E. So this is just what we did before. We're taking E and we're subtracting off this O minus n. But the difference is before, this map was an injection and we just took the co-kernel. Now, because E has rank 0, this map is neither an injection nor a surjection. So it has kernel and co-kernel. So this is really a non-trivial complex of sheaves. It's not quasi-isomorphic to its co-kernel sheaf or anything like that. Okay, so we replace E by these complexes of sheaves. These are rank -1 because E is in degree 0 and O minus n is in degree -1. Okay, so rank F is -1 now. Its churn characters given as before. Oh, I've got 2 slides, I beg your pardon. This is the last slide. However, the derived dual of this F, so we can just dualize this guy. So I can replace E by its, well, let's not go into what derived dual means. But anyway, there's a way of dualizing this guy. So I replace E by its dual, really its derived dual, and O minus n by its dual, which is On, and I get the section going in the opposite direction. This has rank 1. So this is in degree 0, and this is in degree 1. Did I say that right? I'm confused by, I've confused myself by some degrees, but anyway, this has rank 1. And after some wall crossing, it becomes a stable pair. So these things are very closely related to ideal sheaves. They're also complexes of sheaves, but you can think of them as almost being ideal sheaves. Because Bridgeland and Toda have already done their wall crossing from stable pairs into ideal sheaves, proving that stable pair invariants can be written entirely in terms of rank 1 DT theory, so ideal sheaves, MNOP invariants, or again, Gromov-Witten invariants. Okay, so, and this dualization doesn't change any invariants. Obviously, it doesn't change moduli spaces. So these rank -1 objects are equivalent essentially to rank 1 objects that we already understand. We already know how to write in terms of Gromov-Witten invariants. So the rough idea in this case gives a simple universal formula relating these rank 0 sheaves to rank 1 DT invariants and therefore curve counts. And, you know, there's lots of correction terms to check, but we already have, you know, the induction starts. So we can show that whenever the destabilizing object across a wall also has rank 0, then its D4 part is a sheaf of smaller degree. So the as you wall cross, the worrying thing would be if you wall cross and you start, your shrapnel that you split off has higher degree. That is quite possible in these categories and with these stability conditions. But we can show that actually it has strictly smaller degree. So that the induction starts and we can get going and control the higher order terms. So hopefully in a month or 2, we'll be able to show that all rank DT invariants can be written in terms of rank, not just rank 0 invariants, but they can also separately be written in terms of rank 1 invariants or abelian DT theory. Okay, I'll stop there. Thank you.
Thank you, Richard. It's a great talk on great progress on a very long-standing question. So if there are questions, you can just raise your hand in the chat. I will ask you to unmute yourself, and you can ask your question. Let me close my chat window so I can see if there are others. Jim has a question. Can you unmute yourself, Jim? No. If you can't, I'll unmute you then.
Oh, there we go. There we go. Okay, I'm determined to say something. No, so to go from the, say, just rank 1 to rank 0 equivalence that you prove. So this is like the digraph-Witten invariants, which have these, modularity, mock modularity properties you talked about, to Gromov-Witten invariants. You expressed your general formula in terms of like universal polynomials for individual invariants, but of course, what you really like is some understanding of the whole partition function. So if you unpack your argument and say, like, what is the Gromov-Witten partition? Well, or ordinary DT partition function. What is your formula? How does that relate to the digraph-Witten partition function? And then is there some way to get control over the modularity properties from a formula like that?
Yeah. So yeah, that's an issue. Somehow, because what we're doing is uniform, like we're doing the same thing to every sheaf, right? We're taking this O minus n and so on. Then it turns out that the problem that I think you're raising is not such a problem. So the functions are basically the same for different classes, or similar enough for it not to be a problem. The problem is that the amount, you have to choose this little n to be very large. And for a given fixed n, it'll only work for sort of half. If you've got an infinite line of invariants, it'll only work for half of them, right? A half line of invariants. And that is the problem. So at the moment, basically what it means is if you want to see modular forms from MNOP or Gromov-Witten invariants, what you have to do is sort of take half your generating series, like all the very positive bits of it or something like that. And then you would claim that that is governed by modular forms. But the problem is it's a vector valued volume modular form, and the length of the vector is related to n. It's like a power of, it's either n to the 4th or n to the 1/4 or something, I can't remember. So it's hideous, unless you can take n small. But there's a great paper of, so it doesn't sound like a very good way to go, right? But there's a great paper of Gaiotto, Strominger, and Yin, maybe, quite a long time ago now, where they do something which amounts to something rather similar to what we're doing for very small n, and they work in a situation on the quintic where actually that small n will work because there's no higher cohomology and everything behaves nicely and so on. And they actually show that their invariants really do match with certain vector value modular forms, and they use that fact to predict other invariants and get the correct answer. And in a beautiful, I mean, you would love it if you read it. For a mathematician, it's just incredible because they don't get the right invariants, but they get the right invariants to within 1% or something. I mean, can you imagine that in a math paper? That must just be a coincidence, right? But actually, they have good reason why they're kind of 1% out, and they made some approximation somewhere, and whereas we would just think, well, we're dealing with integers, and we made an approximation somewhere, and we got the wrong answer. But it turns out that they think there's some sense in which their approximation wasn't too bad, and indeed the correction is small in some sense. It's really incredible. It's really impressive. So so it's not obvious that this relationship between these two types of invariants is much use, but their example seems to show that actually it's worth considering, and mathematicians ought to have a go.
Are there other questions? So I have a question. So beyond trivial cases where you have a virtual projective space structure or projective space structure comparing rank 1 and rank 0, are there any nice classes where you can really compute these universal expressions explicitly?
Yeah, I'm the, me, Sheldon, I'm the wrong man for that. Yeah, I'm sure there are, definitely. But I haven't done it, and I won't be doing it. So okay. I'll be wallowing in my abstract nonsense.
Okay. Well,
I don't want to be doing calculations. I'll leave that to Jim.
Yeah.
I have a tangential question. So you mentioned this paper of that's also Nekrasov, Kesselunga, and Zebzin. That talk about some factorization of
Yes.
these high-rank DT invariants.
Yes.
There, like, can you see that in your story, or can you comment at all about the relation to what they do?
Yeah. So in fact, I only heard about this paper today, so no. I just consider it completely orthogonal to what we're doing, in the sense that I think there's basically no way we would be able to see even explicit formulae, never mind factorizations or anything as nice as that. So I consider, what we're doing is some kind of abstract existence theorem, and then the question becomes to find a formula, and then of course it makes perfect sense to compute in the toric case. And my understanding is, although I have almost no understanding, but my understanding is that probably they've done that computation in the toric case, and therefore that could tell us what these functions should be. And hopefully their formulae make sense in the non-toric case and are still correct. But yeah, it's a great question, and I don't know the answer really.
Thanks.
Are there other questions? Well, if not, then let's thank Richard again for a great talk. Thank you, Richard.
You. Oh, someone has their hand up.
Oh, I'm so sorry. I didn't.
Maybe they may have hit it by accident. Now they don't have that.
I don't see it. Okay. Anyhow,
Yeah.
it stopped recording, so you can say whatever you want to now.
So now we can really grill him.
Now we can.
There must be some cases actually that just reduced to things that were previous known. For example, if you just had a churn character such that it looked like a bunch of points and then some higher rank, so the same. Like higher rank D zero dimensional. I forget what people call this, but people have studied this in the past. Were you able to recover those results, or is that sort of just too silly a case from your point of view?
No. I mean, someone should do that. We just haven't tried, but yeah, absolutely, you should be able to do that, and it'd be a really good calculation to do. Yeah.
And in general, going from super high rank to lower rank, if you were writing things down on partition functions, you would involve acting by exponentials of operators of Poisson, all this terrible stuff in that wall crossing formula in general, right? But if I understand what you're saying, just going from rank 1 to rank 0, you avoid all that somehow, even though the Euler pairing isn't 0, right? I normally think of wall crossing being easy when the Euler pairing is 0 and hard when the Euler pairing is not 0. But you're saying somehow even in that 1 to 0 case, you avoid all that.
That's right, and it's not because of the wall crossing formula. Absolutely, it's because there's no walls. Yeah, it just for a very large n, we just surprised ourselves by finding that this Bogomolov-Giesecke conjecture implied eventually, through a lot of work, that there were no walls other than the Joyce-Song wall. As you pointed out, so yeah.
So I still have a hard time seeing why you can't get then explicit. I think you explained it, but explicit formulas for the partition functions between the two.
Well, I like to calculate, and that sounds terrifying to me.
Wow.
Because as you change the curve class or the number of points, you may have to increase n. That's the problem.
It's the same
with the fixed n. For fixed n, you can only handle half the curve, or all the curve classes below a certain point or something like that. Low degree curve classes. A bounded number of free points. That's the problem.
And so if you put in the n with a new variable in your partition function, you saying you still can't get a relation between these partition functions?
No, that's a good idea. That's a good idea. Yeah, possibly.
Yeah, that's what Joyce and Son did, is in terms of the keeping n in there.
Also, remember this n is related to the length of the vector. You're supposed to produce vectors and produce vector value modular forms. So
I see. Yeah.
So it becomes pretty nasty.
You get some theta function in there.
I don't know. Must be on me. Hey, it's frightening giving seminars nowadays. You realizing you're on YouTube forever. God.
Well,
can I go back and ask for bits to be cut out? I don't. I'm joking. Of course.
You can. No, you can if you want to.
Wow. Yeah, it's frightening. It used to be so easy. You could swear and make mistakes, and there'd be 10 of your mates listening. And now,
no, it's been painful listening to some things where I've had live lectures recorded and I didn't realize the mic was still on. But so anyhow, yeah. So when I said that